So today I'm going to talk about the main topic of my thesis, which is EEL tomography. So the idea behind this electron energy loss spectroscopic tomography is to bring together chemical information from EELs, which has already been introduced in the previous talk, and 3D reconstructions from electron tomography. So just to start, EELs. So the EEL signal arises from interactions from the electron beam in the transmission electron microscope with the sample. And from these transitions we can get the chemical information we are interested in. And then we also have the electron tomography in the transmission electron microscope, which consists in acquiring a series of images at different tilt angles and then just projecting them back to get this three-dimensional reconstruction. So this is one example of the particles I'm going to use as an example for all this technique. So here we have just, we have no chemical information, we have structure information. So let's go and try to combine both of them. So starting with the acquisition, not all signals in the electron energy loss spectrum can be used. So we are just based in the core loss transitions from, transition from core loss to empty states, because it's the intensity under this signal just changes monotonically with one property of the sample. So this signal can be reconstructed. Then just see what we got. Our sample was a cobalt and iron mixed oxide mesoporous nanoparticle, and we acquired this signal very fast. So we had very noisy data. The problem behind this technique is that we have to acquire about 50 different images, and each of these images might take several minutes or to acquire. So the whole thing takes a lot of hours. So we just did this very fast. So we have a lot of noise. And what we wanted is just to get clean spectra. So we applied principal component analysis, which, summing up very fast, separates components according to their variance. And we just keep these five first components. We have most of the signal. And then we have clean spectra. So you already see the difference between before the treatment and after the treatment. And it's this multivariate analysis technique that enabled us to perform EEL tomography in the transmission electron microscope. Again, we extracted the intensity. So these are some maps from oxygen, cobalt, and iron. We can do even more things. We can do independent component analysis, which is quite similar to principal component analysis, but in this case, we separate the components according to their independence, and here we have just three components that clearly correspond to, in green, to the thickness of the sample, in blue to iron oxide, and in red to cobalt oxide. So we reconstructed all of these samples, and we even combined some of these signals just to obtain this third signal combining